All right, here we go into lesson 5.8 where we are going to learn about integrals of inverse trig functions. Now, this is usually pretty difficult to do when taught with a textbook that doesn't connect ideas, but remember, I want you using the formulas that I taught you in 5.7, our lesson 5.7, so that you can see the connections here. It's very simple that way. We know the derivative of arc sine of u over a is u prime over root a squared minus u squared. So if we take the integral of that same exact content, right, something of that setup, then we're going to end up with arc sine of u over a. It's just going backwards, plus c. Here we have u prime over root a squared minus u squared. So its antiderivative would be what the original function was. So the derivative of this is that. So that's the antiderivative. Very simple. So if you're given au prime over a squared plus u squared is the derivative of arctan of u over a, the derivative of this is not quite arctan. What we need here, because you're often going to be given an antiderivative that looks like this, is we need an a here to look exactly like this. And so then that would give us 1 over a to balance it out, just like with u substitution, right? Ooh, well, now you've got au prime over a squared plus u squared. So the derivative of what is that? The derivative of arctan. And so we have that 1 over a chilling out. Arctan of u over a plus c. And so now you see why in your formula, in your textbook, it's that 1 over a. That explains that. Same thing here. The derivative of arcsecant is au prime over absolute value of u over root u squared minus a squared. So the derivative is that. So the antiderivative, we don't have an a there. We often won't. So I'm going to put an a and a 1 over a just like before. So what's the antiderivative of this? Or the derivative of what is that? Well, here it is, the derivative of arcsecant. So that's going to be arcsecant of u over a plus c. Don't forget about that 1 over a and how that comes from this little bit right there to get it to look exactly like this. Again, that 1 over a comes from the fact that most antiderivatives, most integrands, won't have the a in it already. And I think that explains nicely why it is that we've got the 1 over a in both those pieces. So you could memorize these, or as long as you've memorized these formulas we've gone over from 5.7, when you recognize them in the antiderivative, you get them in that form, you immediately revert back to the derivative. So it's kind of like, oh, you got cosine in the integrand, so the derivative of sine is cosine. So recognize your derivative in the integrand and go back to what you know. So it's knowing your formula forwards and backwards. Now, quick note I put down here. Arc cosine, cotangent, and arc cosecant are often used, not used in integration. The reason being is they just got the opposite sign. So if I'm given this and I've got like a negative sign here, I'm just going to pull the negative sign out and still have arc sine just with a negative. So we're often not going to be taught arc cosine, arc cotan, or arc cosecant for that reason. You can just pull out the negative. So that's that. Just know those three and you'll be in good shape. All right, let's exercise them now. So this says find the indefinite integral of each. We'll do 3 problems and then we'll call it a video. Okay, so with this one right here, I'm going to factor out that 2, right? Always factor out the coefficient. You're left with dx all over, or 1 dx all over the square root. And what I start to do is I recognize this is a squared. So that's 3 squared minus x squared. Well, I like to rewrite this as a template. It makes life easier. So I've got 2. I've got in the bottom there the square root of, let a equal to 3, right? Because that's a squared. U would be equal to x. Okay, see where this is going. So u is equal to x. And then therefore du is equal to dx. So we're literally just subbing in. So I write it exactly as the template formula that we saw on the last page. A squared, boom, u squared, and then dx is du. So now all I've got to do is recognize that that is exactly arc sine. So this is 2 arc sine of u over a. So u over a plus c, and then we'll plug in 2 arc sine. So it's almost like u substitution. That's just to fit our formula. So arc sine of u, that's x, over a is 3 plus c. And you're done. And you could check your answer by taking the derivative. Again, get it to look like the template form, and then you're like, wait a second. This is exactly what the formula is. We can do that every time. So we'll do it again here. In this problem, what we have is we've got something that's close to arctan. So this I'm going to rewrite as, well, we've got that dx. We'll take care of that in a second. And then this is going to be, well, we've got a 5 here. So that'll be root 5 squared. That's a squared. And then we've got plus 2x squared. All right, looking at it like, ooh, this looks like it could be arctan. Don't immediately go into arctan or arcsine, by the way. You're doing this if and only if no other functions or no other processes work. So you've gone through u sub, you've gone through other ideas, and then you're like, wait a second, this looks like it could be arcsine, or this looks like it could be arctan. Then we go there. This is u squared. So a is equal to root 5, u is equal to 2x, and du is therefore equal to 2 dx. Now we don't even have a 2 dx, so I'm going to throw that in there. So now I've got 2 dx, a 1/2 to balance it out there. So now I've got 1/2 the integral of du all over a squared plus u squared. And now just follow the formula. Well, this is going to be equal to 1/2 times 1 over a arctan of u over a. Not bad. Plus c. Right? So get it so that it looks exactly like the formula, and then you're rocking this thing. So 1/2 times 1 over a, that's 1 over root 5, I've already identified that here, is equal to, not equal to, is multiplied by arctan of u over a. U is 2x. Sweet. All over a, root 5, plus c. And we can simplify that a little bit more, I guess. 1 over 2 root 5. Arctan, if you really want to take a derivative of this to check, be my guest. Arctan of 2x over root 5 plus c. Nice. All right, we got one more problemo. Let's do it. And in this problemo, we've got the indefinite integral of that. Ooh, that one looks like, I don't even know what to do there, right? Well, u substitution's not going to work. However, it looks a lot like arcsecant, right? And if you remember, arcsecant's formula is pretty gnarly, but it's this. Get the integral of du all over. You've got some form of u, and then you've got the square root of u squared minus a squared. It kind of resembles that. And remember, that's 1 over a, and that'll be arcsecant of u over a plus c. All right, so we're kind of like that. How do we fit that mold? Well, you've got 4x squared minus 5 squared. All right, so that's pretty gross to start. This would be u. This is going to be a. Where does the x come in? Patience. Patience. We'll get there. So looking at this, what I have right now is I've got some nastiness with that 4x. We'll deal. So I've got u is equal to, ooh, how are we going to deal? Well, u is equal to 4x. Du is equal to 4 dx. Now I don't have that 4 dx. Check out what's going to happen in a second. To get that 4 dx, I'm going to put a 4 there and a 4 in the bottom. And you might be like, why put it in the bottom? Because look what we now have in the bottom. We have u. Isn't that tricky? I think it's really tricky. It makes it difficult. So a is equal to 5 as well. And so now we just plug and chug. So 4 dx is du. We have that. All over. What's 4x? It's u. So you've got u times the square root of u squared minus a squared. And so now we've got the exact template. So we're going to get 1 over a arcsecant, that's difficult, of u over a plus c. Okay, so now from here, 1 over a is 5, 1/5, arcsecant of u over a. So that would be of 4x all over a plus c. Answer. So the difficult part there is knowing to let u equal to 4x. When you do that, however, oh man, we're doing the normal old u substitution, but knowing to keep that 4 in there, then you get the actual u value back, the exact u value. And when you sub it in, you get it in that template form, you're like, oh, I'll just use the formula. And you plug in and chug. All right, that's it on this one, how to integrate inverse trig functions. In the second video, I'm going to go over what to do when you actually have to complete the square, which is gnarly. I'll see you there. Peace.